consequences if you want to get a more in-depth study in the field. Now, let me give you a very hand-waving argument why you can do things with spin currents differently than what you can do with charge currents. Now, as it's often the case with hand-waving arguments, is they're not completely correct in detail, but they give you the right idea. If you really want to know how to do it correct in detail, you can look at this paper, but this paper is much more complicated than what I'm telling you in the next minute. So if you think about the charge current essentially is nothing else but the time derivative of a charge distribution in space. And we know that charge is a conserved quantity. Therefore, what a charge current is it's nothing else but a charge moving with some velocity. And so we know that, I mean, we use drift diffusion equations and things to describe charge transport in solids. And now, a spin current, you can think of it essentially very similarly. You say, okay, it's this time derivative of a spin distribution in space. But now spin is more complicated than charge, right? Spin is a vectorial quantity, and as a whole is not conserved. The magnitude of the spin is a conserved quantity, but its direction can change. And therefore, if you look at this time derivative, you get two contributions. You get one where the spin just moves with some velocity, the same way how the charge moves with some velocity. But you get another contribution to spin currents that comes from just the dynamics of spins. Now, it's easy to see how we get a spin current from a moving spin, right? We just have a spin, that goes from one place to another. I mean, just like a charge goes from A to B. How do we get spin currents from this spin dynamics? Well, I'll give you a very simple example that some of you may be familiar with. Let's imagine you have a ferromagnetic material where all the spins are all aligned to each other. Let's say they all point up. Now what you can do is you can flip this first spin here. What you create is a so-called domain wall, where on one side of the domain wall the spins point in one direction, on the other side they point in a different direction. Now what can happen is this domain wall can move through this material by flipping one spin after another. And what you see is that you can get a spin current moving spin down from one side to the other side, but you never actually move any of the spins in space. You just flip one after another. And if this process of flipping a spin can be done with less power dissipation than the process of moving a spin, then this is